Ever clicked a paint bucket and watched color spread perfectly through a region? That's flood fill, a pattern mastery 100 staple that tests if you can control recursion/iteration, guard edge cases, and traverse grids cleanly. Interviewers love it because one tiny bug creates infinite loops. Today, we'll nail it with basics so your solution is fast and bulletproof. Let's break it down. We're given an image grid, a starting cell, SR, SC, and a new color. We must recolor all four directionally connected cells that share the starting cell's original color. If the original color equals new color, nothing changes, return the image. Now let's assess it. This is a classic graph traversal on a grid. Use DFS or BFS. Watch two pitfalls. If new color equals old color, early return to avoid infinite revisits. Stay inbounds and only traverse cells with the old color. Complexity is OM middle.n time, OM middle.n space worst case, stack/q, for an M times n grid. Here's the structure. Plan with BFS, iterative and interview friendly. Read old equals image SRSC. If old equals new color, return. Push SR, SC, into a queue and recolor it immediately. While queue not empty, pop R, C, for each neighbor, near, NC, in 4 durs. If inbounds and image near NC, equals old, recolor and in queue. Let's try to implement it using solution 1. Line highlighted. Class solution. First, we define a class called solution. You can think of this as the box that will hold our flood fill logic. Line highlighted. Private int original, new color. Here we declare two private variables. Original will store the starting pixel's original color, and new color will store the color we want to paint with. Keeping them as fields makes it easy to reuse them in our helper function. Line highlighted. Private int m, n. These two variables, m and n, will hold the height and width of the image. They help us quickly check boundaries without recomputing lengths every time. Pause. Line highlighted. Public int, flood fill int, image, int sr, int sc, int new color. This is our main method, flood fill. It takes image, a 2D grid of pixels, each pixel is a color value. SR, SC, the starting row and column. New color, the color we want to fill with. It returns the updated image after filling. Line highlighted. This.m equals image.length. We set m to the number of rows in the image. Think of m as how tall the picture is. Line highlighted. This.n equals image 0, length, and n becomes the number of columns, how wide the picture is. Line highlighted. This.original equals image SR/SC. Here we capture the original color at the starting pixel, SR/SC. This is the color we are going to replace in all connected neighbors. Line highlighted. This.new color equals new color, and we store the desired new color into the class field so other methods can use it easily. Line highlighted. If original equals new color. This check prevents unnecessary work. If the original color is already the same as the new color, there's nothing to change. We only proceed if they are different. Line highlighted. DFS image, SR, SC. If the colors differ, we call a helper function DFS starting from the given row and column. DFS stands for depth first search, and it will recursively paint all connected pixels that share the original color. Pause. Time complexity note. The flood fill process can potentially visit every pixel once, so the overall time complexity is OM times n. In the worst case, where m and n are the dimensions of the image. Line highlighted. This closes the if block. Line highlighted. Return image. Finally, we return the modified image after the fill is done. Line highlighted. This closes the flood fill method. Line highlighted. Private void DFS int, image, int I, int j. This is our helper method DFS. It takes the image and the current pixel position, I, j. It doesn't return anything. Instead, it directly updates the image in place. Line highlighted. If I less than 0 vertical bar, j less than 0 vertical bar I, greater than equals m vertical bar j greater than equals n vertical bar image ij, equals original, return. This line is the base case for the recursion. It stops the fill when I or j are out of bounds, we went outside the image, or the current pixel's color is not equal to original. It's either already painted or a different region. If any of these conditions are true, we simply return and do nothing more from this path. Line highlighted. Image ij equals new color. Here we actually paint the current pixel. We change its color from original to new color. This is like dipping your brush on this pixel. Line highlighted. DFS image, I+1, j. Now we move down from the current pixel and recursively try to fill that neighbor. line highlighted, DFS image, I1, J. Then we move up from the current pixel and try to fill that neighbor as well. Line highlighted, DFS image, I, J plus 1. Next, we move right from the current pixel and fill that neighbor. Line highlighted, DFS image, I, J, 1. And finally, we move left from the current pixel and fill that neighbor. Together, these 4 calls explore all 4 directions, up, down, left, and right, spreading like paint to all connected pixels of the same original color. Pause. Time complexity note. For DFS, each pixel is visited at most once, and each visit does a constant amount of work, checking conditions and making up to 4 recursive calls. Overall, this DFS still runs in OM times n, time in the worst case. Line highlighted, this closes the DFS helper method. Line highlighted, and this closes the solution class. Final wrap-up. And that's how this algorithm works. It first records the image dimensions and the original starting color, then uses a depth-first search to recursively repaint all connected pixels that share that color, exploring in 4 directions. Efficient, simple, and elegant. Highlight input box, image equals 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2. Here, we start flood fill at position 1, which currently has the value 1. Our job is to recolor this pixel, and any connected pixels with the same value, to 2. Explain briefly, the pixel at 1, 1 connects to a whole block of ones around it. Up, down, left, and right. All of these connected ones get changed to 2. Pixels that are diagonal or blocked by a different number, like the zeros, are untouched. Highlight output box, 2, 2, 2, 2, 2, 0, 2, 0, 1, and that's exactly the result. All connected ones were replaced with 2, matching the expected output. So the flood fill works correctly, spreading outward from 1, 1, and recoloring only the valid connected region. Let's try to implement it using solution 1, but this time we'll narrate solution 2, the BFS, Q-based, version of flood fill. Line highlighted, import java.util. We import Java utilities so we can use helpful structures like Q and linked list. Line highlighted, class solution. We begin the solution class where our flood fill logic will live. Line highlighted, public int, flood fill int, image, int SR, int SC, int new color. This method updates a starting pixel and all connected pixels of the same color, spreading outward like paint. Basic setup, line highlighted, int m equals image.length, m is the number of rows, how tall the image is. Line highlighted, int n equals image 0, length, n is the number of columns, how wide the image is. Line highlighted, int original equals image srsc. We store the original color of the starting pixel. Only pixels with this color will be replaced. Line highlighted, if original equals new color, return image. If the starting color is already the new color, there's nothing to do. We return immediately to avoid unnecessary work. BFS initialization, line highlighted, qint greater than q equals new linked list. We set up a queue for a breadth-first search. This lets us process pixels level by level, like ripples spreading outward. Line highlighted, q.offer new int srsc. We add the starting pixel into the queue. Line highlighted, image srsc equals new color. We paint the starting pixel right away. Directions array, line highlighted, int ders equals 1, 0, 1, 0, 0, 1, 0, -1. This array represents the 4 neighbors we can move to: down, up, right, and left. BFS loop, spread the color, line highlighted, while !q. is empty. We keep processing pixels until no more connected neighbors remain. Line highlighted, int cell equals q.poll. We take the next pixel out of the queue, the next ripple center. Line highlighted, int r equals cell 0, c equals cell 1. We extract the row and column of the current pixel. Check all 4 directions. Line highlighted, for int d ders, we loop over each possible direction. Line highlighted, int near equals r plus d0. Near b is the row of the neighbor we want to explore. Line highlighted, int nc equals c plus d1. nc is the matching column for that neighbor. Line highlighted, if near greater than equals 0 and near less than m and nc greater than equals 0 and nc less than n and image near nc equals original, we check 3 things. The neighbor is inside the grid. The neighbor's color matches the original starting color. That means it should be painted and added to the BFS wave. Line highlighted, image near NC, equals new color. We paint the neighbor with the new color. Line highlighted, q.offer new int near NC. We add this neighbor to the queue so it can spread the fill further. Line highlighted, end of the condition. Line highlighted, end of the loop over all 4 directions. Line highlighted, end of the BFS loop. At this point, there are no more matching neighbors to process. The flood fill is complete. Return final image. Line highlighted. Return image. We return the fully updated image. Line highlighted. End of method. Line highlighted. End of class. Time complexity note. Each pixel is processed at most once, added to the queue once, and visited once. This gives us a time complexity of OM times n, where m and n are the image dimensions. Final wrap-up summary. And that's how this algorithm works. It first colors the starting pixel, then expands outward using a BFS wave, painting all connected pixels with the same original color until there's nothing left to spread to. Efficient, simple, and elegant. Highlight input box. Image equals 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2. Here, we start flood fill at position 1, which currently has the value 1. Our job is to recolor this pixel, and any connected pixels with the same value, to 2. Explain briefly. The pixel at 1, 1 connects to a whole block of ones around it. Up, down, left, and right. All of these connected ones get changed to 2. Pixels that are diagonal or blocked by a different number, like the zeros, are untouched. Highlight output box, 2, 2, 2, 2, 2, 0, 2, 0, 1, and that's exactly the result. All connected ones were replaced with 2, matching the expected output. So the flood fill works correctly, spreading outward from 1, 1, and recoloring only the valid connected region. Ever clicked a paint bucket and watched color spread instantly across a region? That's flood fill, a perfect test of clean grid traversal, recursion control, and edge handling. Let's do a recap. We're given an image grid, a start cell, and a new color. The task: recolor all connected cells, up, down, left, right, that share the starting color. If the starting color already matches the new one, we simply return the image as is. It's a classic graph traversal disguised as painting. We can use BFS or DFS, both work. The main pitfalls? Avoid infinite recursion when the color doesn't change, and stay inside bounds at all times. The plan: record the starting color. If it's already the new color, stop early. Use a queue, BFS, to recolor the start cell and expand to 4 directional neighbors with the same color. Continue until no connected cells remain. We executed this BFS plan, handled edge checks, recolored properly, and ran it on LeetCode with 0 errors. All test cases passed. Traversal and recoloring behaved exactly as expected. The big lesson: flood fill isn't just about color, it's about control. Managing boundaries and revisits cleanly proves you understand traversal flow from start to finish.